Alright, good morning class 2. Okay, today we will move on to A-Maths. So I hope you have your A-Maths textbook as well as your A-Maths worksheet with you. Right, so today we'll go on to start chapter 15, rates of change. And actually rates of change is a continuation or rather an application of what we have learned earlier on differentiation. Okay, so if you recall, I've told you before, the differentiation of a function can also represent the rate of change of a function. Okay, so earlier on when we started learning the differentiation of a function dy dx, we know that the dy dx of a graph at a point also represents the tangent, sorry, not the tangent, but the gradient of the tangent of the graph at that point. Right, so for instance, if I look at the curve that's shown over here, at this point A here. Okay, if you look at the tangent is shown here. The gradient of the tangent is downward sloping, so we know that the gradient is therefore negative. Since the gradient is negative, and remember dy dx also represents the gradient of the function, so we know that dy over dx must be less than 0. And therefore we can see that, okay, you can also see that the general slope of the graph is actually downward sloping. So at the point A, we can say that the graph or the function is decreasing. Okay, so when we want to show that the y value, you can show that generally at point A, okay, the y value is decreasing. Therefore, we can say that the function is actually decreasing at point A. Now, what if we pick a point B here? Okay, if you look at the point B, the tangent is shown over here. You realize that the tangent is different. We find that over here, the tangent is actually upward sloping. So since the tangent is upward sloping, the gradient of the tangent must be positive. And recall dy dx also represents the gradient. So if the gradient of the tangent is positive, dy over dx must be more than 0. Now if you look at the point B here, you find that generally the graph, okay, is going upwards, okay, as shown by the direction of the tangent. So we can also say that at B, the graph is actually, sorry, not decreasing because it's upward sloping, it is increasing. Okay, so you can see that in general, when dy over dx is less than 0, we can say that the graph or the function is decreasing. And if dy over dx is more than 0, we can say that the graph is increasing. Okay, how will we apply this? Let's look at the worked example. Okay, look at example 1 here. Now consider the function y equals to x cubed. Okay, over here they just want to consider this function for x greater than 0. Now I hope you can remember, okay, even though the graph is shown here, how to sketch the graph of y equals to x cubed. Now you're asked to show that dy over dx is always positive for x more than 0. Okay, so let's work it out. How do we show that dy over dx is positive? Let's try and work out dy over dx. So we know y equals to x cubed. Now you should be able to differentiate this very quickly. So you find that dy over dx is actually equals to 3x squared. Now we're supposed to show that it's always positive for x greater than or equals to 0. Now look at x squared here. Now x squared, no matter what, is always positive, right? That we know. So we know that 3x squared must therefore be more than 0 for x more than 0. In fact, it is more than 0 for all values of x. But in this case here, since they want it for the range for x more than 0, so okay, we just need to prove this. Therefore, we can say that dy over dx is always positive. Now, what does this imply when we say that dy over dx is positive? Remember, we've learned earlier, if dy dx is more than 0, we say that the graph is increasing. So therefore, this implies that the function is increasing for x more than 0. So just remember, this is an increasing function because dy over dx is more than 0. Basically, we're trying to show that the rate of change is always positive. So from the above example, you know that a function is known as an increasing function if dy over dx is more than 0 within that range. Now, if you look at the graph here, you can see that, that is the case also that dy over dx is always positive, because if we try to draw a tangent at any point, whether any point you try and draw a tangent, you realize that the tangent is always upward sloping. And this corresponds to the fact that dy over dx is always positive. Alright, so to check your answer, you can always try and sketch the graph if you know how to sketch the graph. Now, let's look at another example. Example 2. Now, in example 2, you are given another function, for a specific range, x more than or equals to 0. And this time round, you're supposed to show that dy over dx is always negative. Alright, so let's try now to work out what dy over dx is. We know y equals to 1 over square root of x plus 1. And to simplify this, I can write this as x plus 1 to the power of negative half. So we can use the chain rule to differentiate this. So dy over dx, remember what you always do. Bring down the power. Keep the inside. And then the power, you need to minus 1. So you get negative 3 over 2. And then we differentiate the inside where we get 1. So you actually get negative half x plus 1 to the power of negative 3 over 2. Which gives us, negative 1 over 2, right? X plus 1 to the power of 3 over 2. Now remember, we want the range x more than or equals to 0. So if x is more than or equals to 0, we know that x plus 1 will definitely be positive. Right? Because if you take a positive number plus 1, it becomes positive. And therefore, we know that if we take a positive number to the power of 3 over 2, alright, it will still remain positive. And therefore, if you take 1 over x plus 1 to the power of 3 over 2, this is still positive. And if you multiply it by negative half now, if you multiply this by negative half, you find that what is always positive now becomes always negative. So you can see that dy over dx is always negative for x is more than or equals to 0. You can actually put a shown over here already. And therefore, if you know that dy over dx is less than or equals to 0 for x more than or equals to 0, then this implies that, remember we're supposed to show what does this imply. So this implies that the function is a decreasing function. So it should be decreasing here. In fact, if you want to be strict about it, we can even remove the equal sign, because if you know that if x is positive, then x plus 1 must be more than or equals to 0, and then you can actually remove all the equal sign, and you get, sorry, this is given, so we still have to keep this. You get dy over dx is less than 0, which is always negative for x more than or equals to 0. So we see that this is a decreasing function. Now can move on to go on and try exercise 15.1 question 2, 5 and 6, and after you finish those you can move on to your homework question.